Welcome, statistics humans, to another stats video. Today we're going to be talking about confounding variables. So a confounding variable is something in an experiment or a simulation or a situation that we're observing that could be the cause of a change that might not be the same cause that we think. So just a real quick example, like off the top of my head. Um, if you're looking at like crime statistics and you see that crime goes up when the temperature goes up, um, or yeah, so crime goes up when the temperature goes up. So then you say, okay, well, when crime goes up, I see that ice cream sales also go up. So does crime have any impact on ice cream sales? Well, not really. It's just that it's hot out and people are more willing to go outside and do bad things to other people. So that's really one of those confounding. That's one of those confounding variables. One of those things that can be causing some problems when we are trying to look at situations. So this is why we can never really say this actually is the cause. This is exactly why this happened. The only time we're allowed to say that is if we actually do a proper experiment, which we'll talk about later. But for right now, we're just looking at hypotheses and situations. So confounding variables are other contributing factors, are things that could contribute to a situation that might change without being the cause of that change. Okay. So, for example, we have the Cincinnati Reds this year. They're not doing so hot. Their total they're 21 and 26. It's still good enough for third place in the NL Central, but still not super great. Right now, they're not looking too hot for the playoffs. But we've say we did a study and we found that when they look at and when they wear red jerseys, they win eight. So far, when they wear red jerseys, they win 8 times and they lost 11 times. But when they wear gray jerseys, they win 13 times and 15 times and lose 15 times. So this would give them a record of 8 and 11, or 8 out of 19 of their games would be wins when they wear red, and 13 out of 28 of their games would be wins when they wear gray. So if we take a look at a graph, that would say, okay, well, their win percentage when they wear red is lower than when they wear gray. And when they wear gray, it's actually higher than their total win percentage. So we might come up with some hypotheses. Okay. Just in general, we would probably think that jersey color wouldn't matter at all when it comes to whether a team is going to win or lose. But here, it kind of looks like it might. So our null hypothesis, our statement where nothing would happen, would be something like this. The Reds' ability level doesn't change when they change uniforms. Their ability to play baseball stays the same regardless of whatever color clothes they're wearing. So what we're checking here is that the Reds have a greater ability. Their ability level actually goes up when wearing gray. So essentially we're saying the number of wins that they get when they're wearing gray is not random. They have actually gotten better at playing baseball because they're wearing gray. That's what our alternative hypothesis is saying. Okay, so remember, we're focusing on ability, not performance. All right, so the Reds have the same playing ability whether they're wearing red or gray is our null hypothesis, and then our alternative hypothesis would be that their ability improves or they get better while wearing gray. You could also say the same thing, like they get worse while wearing red, if that makes sense. Okay. So, is this random, or is it an actual ability change? That's our question. Is this random, or is it an actual ability change? So, if we take a look at their red uniforms, by the way, I drew these uniforms. I know. It looks like they're completely like pictures taken off the internet, but I did draw these. And I am super proud of myself, so go me. So if we take their red percentage and we subtract it from their gray winning percentage, so if we do the 8 divided by 19, so 8 games won divided by 19 games played gives us 0.421, and then 13 wins divided by 28 games gives us 0.464. If we take and subtract that, we find that they do 0.043% better in gray. Okay, so that's our difference. So we can take that and say, all right, is that a difference that can be caused by random chance, or is that an actual ability improvement? And one way that we can check this is by running it through an applet, a simulator, which I'll link here. I'll link in the description for this, or I'll link in Classroom probably. So what we do is you go to the website and it'll look like this. So context one in this situation is our red jerseys. Okay, we plug in the number of successes, so the number of wins, and the number of total attempts. Okay, and then context two is gray. We plug in the total number of successes and the total number of attempts, and then we hit calculate the observed difference in proportions. Once we hit that, we'll see something that pops up that looks like this. That says, here's our proportion of successes for context one, here's our proportion of successes for context two. Our observed difference is 0.043. So that means because of the way this thing works, it always takes context one minus context two. So what this is actually going to be addressing is, do the Reds play worse when they wear red? Which is a similar question, not exactly the same, but it's similar. Similar enough that I don't need to redo this and make a brand new video. Okay, so at the bottom, it will say you're good to go ahead and simulate these. All right, you'll see something looks like this. I forgot to animate this particular picture, so I'll just drag it out of the way. How's that sound? Come out of the way. Thank you. So you'll see this. It'll say simulate some number of differences in proportions and get the differences arranged from smallest to largest. This thing will keep track of all your results until you hit reset. So you can do a bunch. All right, so I chose 1,000 because 1,000 is generally a pretty nice number, and it's also a pretty big number when it comes to this sort of thing. You could easily tack on a couple zeros. It's up to you. So it ran 100 trials, ran 1,000 sort of seasons so far, using those ability levels and that sort of thing, and using those numbers, just like we did with the LeBron James playoff performance. And we got this. We got this nice little curve here where it says our simulated difference in proportions. So like if we go at 0, they won exactly as many games as they lost. If we go this way, this is actually them winning more, and this is them winning less wearing red. Okay? Winning more wearing red, winning less wearing red. So we want to say, well, how many times would they actually just randomly do worse than what we observed? So how many times would they do worse than this current season? So if we put the negative 0.043, which was our observed difference, we want to say how many times are they going to do worse wearing red than they are right now. And if we look at this, it counts them up and says 510 times. There's 510 dots that are less than or equal to the specific value. So over half of the initial number of events ended up with a similar or even worse result than we would expect. So what does this mean? All right, this is where the p-value comes in. Okay, so in this simulation, we have 510 out of the 1,000 trials that resulted with the Reds performing similarly or even worse while wearing red versus when they wear gray. So this means it's time to calculate a p-value. So to calculate a p-value, whoops, I should probably grab a pen, huh? So to calculate a p-value, our p-value is always going to be the number of desired events and that's going to be divided by the number of trials. Okay. Yes, I get it. I'm old. I know this is a hashtag, and this doesn't really mean a number thing anymore, but just roll me. Number of desired events divided by number of trials. So the number of desired events are times that the reds did worse while wearing red, or in that case would do better while wearing gray. Is that okay? That they're both essentially the same statement. So the number of desired times that happened in this case is going to be 510 divided by the total number of trials, and I did 1,000 trials. 1,000 trials, and that's going to be, if we want to convert that into a decimal, that's going to be 0.510. And you can leave that last zero off, but I put it on there because I felt like it. Okay, so if we want to use that to say, okay, well, is it just random and the reds are pretty much the same regardless of their jersey, or is our hypothesis correct that they're actually better when they wear gray? We need some sort of guidelines when we're talking about that. So our p-value in this case was 0.51. The way that we talk about those hypotheses in statistics is, should we reject the null hypothesis and accept the alternative hypothesis, or do we fail to reject the null hypothesis? Okay, there's a lot of negative things here, right? Reject, null, fail. I guess null isn't really negative, but whatever. Reject, fail to reject. Like, there's a lot of negative and double negative things going on here. Essentially, it says if we reject the null hypothesis, we say the statement that everything is the same and things could just be happening randomly, we're saying that is false. That's not true. Then we can say, if we are able to say that, then we can say we can accept our alternative hypothesis. That allows us to say yes, because the thing that said everything was the same is not true. We can now say the thing that we're saying changed is true. And then fail to reject means that we don't have enough information to make that statement, to say that, you know what, it could have just fail to reject means we don't have enough information to say it couldn't have been random. All right, it's so unlikely that it was random that we're going to say that this is true. Essentially, we don't have enough evidence. Think about like a jury type thing. If there is a defendant on trial, the defendant pleads not guilty. All right. If there is enough evidence, if there is plenty of evidence to say that this person did this particular crime, the jury will find him guilty. They will say, yes, we have enough evidence to say that you did this. If there is not enough evidence, they're not saying that they find the defendant not guilty. They're not saying that whoever the defendant was didn't do whatever the defendant was accused of doing. They're not saying that he didn't do it or she didn't do it. They're saying we don't have enough evidence to convict this person. We don't have enough evidence to say for sure, yes, this person did this particular crime. Same idea with these hypotheses. Okay, so we're going to have a couple rules of thumb, a couple things you can use to sort of help sort of guide your making of your decisions. So I'm going to go ahead. I'm just going to hide myself here so that way you can write all this stuff down. I'm going to keep talking though. So the numbers you need to look for are 0.01 and 0.05. Okay. These first two, both reject the null hypothesis and end up with a yes for our alternative hypothesis. They support that alternative hypothesis in that specific context. All right. So if it is less than 0.01, it's super likely. It's very convincing evidence to support that alternative hypothesis. Very convincing evidence to support that alternative hypothesis. If the p-value is less than 0.5, it's not as convincing as 0.01, but it's still enough to say, you know what, this is not random. This is not a random event. It's not just normal. So this is convincing enough to support that alternative hypothesis in that context. If there's anything that's 0.5 or greater, any p-values that are greater than or equal to 0.05, random chance could be plausible. All right, this is essentially saying anything bigger than like a 5% chance of happening. Random chance is a plausible explanation for that difference. That is a possibility. So in that case, we fail to reject the null hypothesis. We have to assume because we don't have enough evidence to say that it's not random, we have to say that it could just be random. So we don't have enough convincing evidence to support that alternative hypothesis. All right. So if we return to our question, our p-value in this case was 0.51. Our p-value is 0.51. Should we reject the null hypothesis and accept the alternative hypothesis, or do we fail to reject? Well, since that p-value is greater than 0.05, that's the only number we care about. If it's at all greater than or equal to 0.05, we fail to reject the null hypothesis. And have to say that jersey color doesn't have any effect on how the Reds play, on the Reds' actual ability to play baseball. So let me come back here. There we go. Hi people. We fail to reject that and say that the jersey color doesn't have any effect on the Reds' ability, or it is not a sort of cause and effect type thing. So if someone decided that their ability did change when wearing different jerseys, saying, their ability does get better or whatever, let's say that we did this and we found a reason. What might be some reasons that could be some confounding variables in this scenario? Okay, what might be some reasons that a team would play better when wearing specific jerseys? So a couple examples that I could think of was, so if they wear red, they only wear red. Wow, it would help if you could actually read this. They wear red when they're at home. This is being particularly bad today. Sorry, guys. Versus gray when they're away. So maybe the Reds play better away from on the road versus at home. Or maybe they play better when they hear the crowd boo versus when they hear the crowd cheer, which isn't exactly a super huge issue this year because not so much of crowds, but you know what I mean. So that could be a confounding variable. That could be home versus away. It could be the pitching rotation could just be coincidentally, happening where their better pitchers happen to play more games when they're wearing gray versus when they wear red. So I want you to come up, see if you can come up with your own confounding variables, and we'll go ahead and just put those in the Edpuzzle thingy. So that's confounding variables and sort of an example of where they would live in a specific observation. So with that, I'm going to leave you guys. Have a wonderful day. I will see you during our lives. We'll have a good time. Have a great one, guys. Bye.